Um, so hello everyone, and good afternoon or good day to everyone, and welcome once again to our concrete summer series of short webinar. It's called Master Your Design. Our topic for today is about prestressed beam. Um, I am your presenter today. My name is Jean Valiente. I'm product engineer for Idea Statica Asia and Pacific, and I am based in Singapore. If you have joined me in the previous webinar, you're already familiar that we are using the GoToWebinar platform. And I also would like to remind everyone that the whole session of this webinar is actually recorded and you are muted by default. As this is a short series webinar, which we have a limited time, I invited everyone to please ask questions. So please type your questions in the GoToWebinar application. And while I'll be doing the demonstration, I have my colleague with me who will answer your questions. And of course, if we will run out of time, we will try to answer your questions via email. So today's webinar is actually the fourth installment of the summer series for beginners. It's called Master Your Design, Prestressed Beam with Openings. We cover most of the common examples that is simple in order for beginners to quickly learn all the basics when they want to use our program Idea Statica. And of course, you can watch the recap of all the recordings of this particular series. The recordings will be available in our YouTube channel and in our support center webpage. So today's topic, just for a quick overview of our agenda, I will briefly discuss about the common method to design this beam with discontinuity. And then I will do the demo for the Prestressed beam with openings, where I'm going to show how the modeling process, applying loads, as well as load combinations. And of course, we are going to lay out the reinforcement as well as the pre-stressing strands. And also the anchorage stress for pre-stressing strands for long-term and short-term losses. And lastly, we are going to interpret the results. No? So before I continue, I would like to have a very quick poll about what's your biggest challenge in designing prestressed beams with openings. So you can select your answers and vote. I will launch the poll now. I will give you a few seconds to select your answers. A few more. I think half of you has voted. So I give 5 more seconds before I close the poll. Then let's show the results. Okay, it seems like more than half of you has already voted. So I guess I can close the poll and try to show the results here. No? So if I share the results, it seems like 69% of you mentioned that you have a challenge designing prestress of whether you have accurate analysis for stress concentration, crack widths, etc. And second place, okay, you have lack of suitable software tools, which makes more sense. And detailing check for USLS, okay, that's fine. This is a good poll. They're fair results, I would say. So let me hide the poll now. And let me go back to my presentation. So one of the traditional approach that very common method to design structures with discontinuity, such as beams with openings, is obviously the strut and tie method. So while this strut and tie method is actually proven method over the years to be effective in addressing ultimate limit state. However, there is some limitations when this one is addressing serviceability criteria. And aside from the tedious and iterative process using this method, the accuracy of the results is actually highly dependent on the engineer's judgment for choosing the right truss model and its layout. So yes, there is it's a proven method for ultimate limit state, but of course, for serviceability, we have some limitations. So let me just go to my demonstration. Basically, I have here an example of the pre-stressed beam with opening. So let's start with the demo code check. For the purpose of this demonstration, due to limited time, we will keep it very simple and have all the information made available to you. So we gather the required parameters such as the size and shape of the cross sections, the concrete grade, which is C50, C50 and 60, and we also have the size and shape of the openings indicated, as well as the concrete cover. And here we also have the required loadings for our beams, which is made available which is mostly concentrated load. And we will make use of this information and apply it into our beam for demonstration. Okay, so I will now close my webcam and proceed with the demonstration. Right, so here I will open up 2D detail. We have here various templates. We have also beams, and we also have prestressings. All have the available templates right here that you can make use of. But for the benefit of our beginners, we will try to model it using general beams and walls so that they will know the process how to do it. So I will make use of this. I will change the concrete grade to C50-60. I will leave the reinforcement as this and prestressing. I will change the concrete cover to 40 as what we have included. So I'm going to click on create. So from here, we now have our detail app open. I'm going to click on model entity to create. Select beam under subdivision. And we will select I shape with haunch flanges based on our cross sections. So here, we're going to modify the shape. So I'm going to type the required sections that we have just put in. 1390. The height should be 1.8. And this one is 1.0. 7T. 200. 125. And 140. So we have already pre-selected our concrete grades. We will leave it as it is. So we have now the shape of a member. You can actually see it in preview, but of course we want to change the size or the length perhaps of the beam. So we have a 22-meter beam. We change that to 22 meters. And I want to apply an opening now. So I'm going to click on model entity again, and I will select opening. So from here, I will change the size of the width from this one to 7.75, and the height is 3.5. And I will assign this to a master layer, a master M1 and a master point 1. So here we have some definitions of master point, which is I will choose 1 in this case. You can choose different master point, but it's up to you to decide. Now, in this case, let's try to use 1 instead. And the insertion point is also under 1. You can choose 8 as well if you like. And here, now I want to introduce some X position 3.8. Of course, we have that information that earlier we have 3.65, so we can place it in the position. Now I can copy this thing to have another opening at the other end. All I have to do is click on copy, and I will change the master point to 2, and of course 2 as well. That's what you can see from here. Then I will change it to negative 3.8. So we have it there. Now I'm going to create another opening. So I can also copy, or I can create another one. So the easiest way is to copy it. And then this time we will select circular opening. So here the diameter is 0.5. And from here I can say I can still use M1 because we are member M1. Now we can choose this time. We can also 8. And insertion point here, either you can use 0 or 9. Here you can just say 0, and from 0 I can say 9. And of course, since we are already at that position where we have making use of the insertion point 8, so we don't need a Z possession already. Okay, and the same thing, I'm going to have copy it, but in this case I would change it to 6, and this one should be -9. All right, now we have completed including all our opening in the member. Now it's time to add the support. So I'm going to click on model entity. I will choose point distributed. I will change the width to 0.5, and I will change the position to 0.25. Okay, half of it. And I will copy it at the other end. So just hit copy. And instead of putting it at the very beginning, I will just change it to from the end. So in this case, our support will be now transfer at the end. And then in this case, I will just deactivate our boundary condition for X. And now we have that. So what we can do now, now that we have our support, we can now specify our loads. So I can click on load case. I can rename this to self-weight for our load case 1. I can copy it to add another load case, which is this example. I will say P for prestressing. But before I will proceed to the load case, let me go back to my presentation. Share it again. So you need to actually understand how the increment works for pre-stressed concrete design. There are actually 3 types of load to be applied in the model. One is a pre-stressing, which is for increment P, and permanent for increment G, and variable for increment V. So if you create a load combinations of each containing load types, the whole portion of pre-stressing load type will be applied into the first increment P. And the same goes with the whole portion of permanent load type for G, which will be applied into permanent load case, and so on for variable load types. So therefore, if you look into this process, in ideal static application, the self-weight must always be defined as a pre-stressing load types, as it acts simultaneously with the pre-string force, which is very start from the very beginning. And if you wrongly assign self-weight as a permanent, you will underestimate some deflections, stresses, or even creep as well. And you might have past checks in your design, but in reality, it's actually failing. So you can see from the graph over there, there is some concrete stress strain diagram, which is implemented in the program. This is for serviceability analysis for short-term and long-term verification. And if you want to dig deeper into this information right here, you can visit this web page and read about this theory behind. So let me end that slide again, and I will go back to my demonstration. So now that we know, for self-weight, I will change this to prestressing. And for prestressing, I will change this to prestressing as well, for the prestressing load case. So now that we have established that one, all I have to do is for self-weight, I'm going to add load impulse, which is self-weight. So now we have that available. So now, time for me to add another permanent loads. Just rename it to this time G. And from G, this is already permanent. I will just have to add loads in this case. We are going to make use of point loads. In our example, we have here the loadings of minus 1.75. I will change this to 0.15 as the effective radius. And I will define it at the edge, on the edge of the beam. And this is at the edge of the top. And I will specify it from measured from the beginning. Of course, I will put it at the center. We have a 22-meter balanced beam. I'll put 11 over there. And we have another loads. All I have to do is copy and change it to the X position to 5.5. And I will change the load to minus 150. I also have another loads here. So all I have to do is copy to make it quicker. Don't have to, oops, sorry. I clicked the wrong one. So all I have to do is copy these loads. And all I have to do is just change, instead of from beginning, I'll put it from the end. And now our loads will be automatically captured. So I now have my permanent loads. Time for me to include variable loads. Again, I'll just have to do is copy. I will rename this to Q, and I will change this to variable. From here, we now have some sort of like a template that is copied from permanent load case G. All I have to do is change this to minus 91, and I will change the same magnitude of loads here as well to minus 71, and the same for the magnitude of load here, change to minus 71. So now that we have this, so we now have our load case. All I can do now is, based on this load case, I can now add some load combinations. I will click on load combinations. I will create load combination 1 for ultimate limit state, and I can also create a copy combination 2. This time I will assign it as a serviceability limit state under characteristic. I will leave activated for crack width check and deflection check. So I'm going to click again another copy. This time I will change it to quasi-permanent, but I will deactivate deflection check this time. You can actually apply as many load cases as you want, but in this specific example, we'll just make use of 3 load combinations. So now it's time for me to add some factors. The partial factors for self-weight. Okay, this is 1.35. For prestressing, I'll put here 0.85. Permanent 1.35. For variable is 1.5. And for prestressing under characteristic, we'll just have to define this 0.95. The rest are the same. Quasi-permanent 5. And here, for the variable, I'll just change it to 0.3. So depending on which code you're using or the national annex you're using, this can vary. So I'll just click on OK. Now we have the load combinations available. And from here, we still have some non-conformities. It says that load combinations does not contain load case or load combination does not contain neither loads nor internal forces. So this is actually for prestressing. So obviously we need to add some prestressing in this member. I will click on rebar assembly. I will choose prestressing. Under prestressing one, we have those parameters. So let me go back to my presentation. Let me share my presentation again. So this is actually our prestressing strand geometry. So the spacing of about 80, 130, 180 from the bottom. And we do have 3 layers of prestressing strands. So first layer is 6, second layer is also 6, and we have the last one is 4 strands. And our anchorage stress is actually 1,300 megapascals. For the prestressing strands, we actually have some in general. No? For prestressing strands, there is 1 or more layers of the tendons or the strands have what you call that debonded length. No? Reason for the debonded length is because prestressing causes high stresses at beam ends. This can actually be mitigated with some common design approach, such as providing some debonded length or some sleeves or plastic sheets, the one that you can see it from the image right here. And we are going to apply this directly into our model based on this info right here. For second layer, we have 750 mm. Third layer is 2 meters. So with that, I will end my slide again. And of course, for the material, we are using the same material right there, 15.7. Prestressing type, it should be selected pre-tension. And the number of strands for our first layer is actually 6 numbers. And the load case must be used here because this is now prestressing. We must use load case P. So for long-term losses for serviceability checks, this is actually the shrinkage and long-term relaxations of the stresses. No? So the percentage actually for this one ranges from 10 to 15%. And here in our example, instead of using 5, let's try to make it 13. And the definition of the bar shape, I will leave it by 2 points. Master, I will change it to M1. Master point, we have here the master point. We will choose 1. And the stress here, this is actually the anchorage stress for precision. You can see it from the notes over there. This is actually the anchorage stress at the point right before release. In our example, we have an anchorage stress of 1,300 megapascal. I will put that 1,300 megapascal over there. This X right here is where we have to apply our debonded length. But for the first layer, we're not going to put in any length over there. So I'll put 80 for the Z direction. And the endpoint from here, I will choose M1. This time I will choose master point of 2, so that it will be right there. This one should not have some length. It should be 0. I will change it to 80. Okay, we now have our first layer. Now I'm going to click on copy for our second layer. This time we still have 6. All I have to do is put some debonded length. From here, I will try to put 750 mm. That's what our specifications have. I will put minus 750 over here because of the end. So now you can see it's actually some debonded length over there. I will change the geometry Z to 130. Same goes here to 130. So it will have now specification like that. So third layer, I will copy it again. This time, the third layer, we only have 4. So I will change that to 4. and the debounded length of the third layer, as we specified, is 2 meters. This one, the geometry of the location of it is now 180. So we have plus 50 mm. Same here, minus 1,000. I'm sorry, it should be 2,000 at 100. And here, 180 again. Now we have our Prestressing completely modeled. So from here, we actually can specify reinforcement, but before we specify our reinforcement, I want to go to the Tools tab, and I want to show and click this Topology Optimization. If I click on Topology Optimization, it will run the calculations for reinforcement design, and let's just give some a few seconds. Typically, this range from will take about 30 to 45 seconds to do some optimization. So it's almost done. Give it a second. Okay, I think a couple more. Okay, so here we have our results for of what we can see from here in this result right here. You can see the compression and tension fields. You can even specify the effective volume, and you can also select just shape the effective volume right there. So 40, go to 40, it looks much better. So this actually aids us in specifying our reinforcement, where to place the reinforcement in an optimized way. So if I go back to my design tab, I can actually specify my reinforcement right there. So let me just go to rebar assembly, and from here I will select group of bars. Group of bars, I will select 20 over there. First layer, I have 4 numbers. Number of layers, only 1. And I will leave it as it is. So from here, you will see that our reinforcement is right there. All I have to do is select the anchorage types at the beginning and the end. And I can copy it again to specify another layer. This time I will choose 12 mm. And I only have 2. And I will specify it from the bottom, but this time I need to choose 170. It's right there. Okay. Again, I will need to copy. This time, instead of the bottom edge, I will put it at the top edge, and I will change the cover from 170 to 140. So I put this over there. And again, I need to copy it as well. 12 this time for layers. For bars and the layers, I will change it from settings so that I will have it on the top. So I have now the reinforcement for top and bottom flange. Now it's time for me to add some reinforcement for the web. So I can just click on copy actually. I will remain 12 mm diameter. So this time I will put it back to bottom. And of course, I want to make use of just 2 bars in a layer. I would change the user value to 350 over there. So here, I have it right there. All I have to do is put the number of layers, and I will change this to spacing 290. Right. You don't have to worry about those bars that is over there because the program will automatically detect where there is boundaries for the bars. Okay, so time for us to provide some reinforcement or the stirrups. So let me just go to assembly bar again. I will put group of stirrups. Here I will change this to 50 and then 3 space to 50 and then 33 times 300. So that will be the spacing. So you can see I have that. All I have to do is copy it. So we have some symmetry. I can just change it from the end. Okay, so now I have modeled the webs. All I have to do is put some reinforcement into the opening. So from here, I will try to put reinforcement, say 12 mm. I will change it to 2. So from here, you can see, and then here I will change to 50. I will change to 500. And for the diagonals, I will change it to say 16. And number of layers, only 2. Of course, spacing is 50. And I would likely make it longer. Now that I have that, I can copy the rest of that to the rest of the opening. So all I have to do is click on copy and change the master. So here I will change the master to 2. Again, copy. I'll change the master to 3. And again, copy. I'll change the master to 4. Okay, so now we have our reinforcement. It's time for me to run the analysis. So we now have all the reinforcement. We try to run the analysis and see whether our beams is okay or not. So if you hit on calculate, the program will analyze the beams. So to save us some time, I have already calculated the results here. So from here, we now have, you can see that the values for the checks for the ultimate limit states are completely verified, but we have some problems with the serviceability under stress limitation and crack width. So let's go directly to this issues right here so that we could address it. So under code check tab, if we go to stress limitation, if you go to concrete, it's the concrete seems like this is okay. This is okay. And if I go to reinforcement, it seems like our reinforcement, we have some overutilizations over here, and we have some overutilizations here as well. So we know what to exactly do based on this information alone. We can clearly see through visualization that this is where the failures comes in. And we know what to do, that we should make some adjustment to our reinforcement. So for the tendons, it seems like we don't have problems with our tendons. You can even select it for long-term and short-term over there. Seems like there's no issues with that. And if I go to crack width, so we have some problems here. It's over from the limits. No? So based on this visualization, we can clearly see where the cracks occur, and we can clearly see where we can put our adjustment for the reinforcement. So what I'm going to do right here actually is obviously the right thing to do is to increase the spacing of the reinforcement for the stirrups, and probably increase or make the trimmer bars longer or size wider or something. So what we can possibly do is I'm going to change this reinforcement right here and just apply some reinforcement. No? So instead of applying it directly from here, I'm going to show you the results that I have already prepared after I put in the reinforcement. Give me 1 second. I will show you the results. So here we have now the results after adjusting after adjusting the reinforcement, the spacing of the reinforcement. So I now have a much closer reinforcement, and you can see that the stress limitation and the crack width are now passing. So if you go to ultimate limit state check, which is under strength, you can see the principal stresses of the concrete. If I go to reinforcement, you can see also the utilization. If I go to stress limitation, you can see there's not a problem there. Our reinforcement is also okay. We now have a much lesser utilization, which perhaps, I guess, we can also a little bit optimize. So if I go to, can actually specify which checks would I for long term or short term. So you can see clearly the difference between a long-term effect and a short-term effect. No? So if I go to crack width, now that we are done, you can also see the results for crack width that after we have modified the reinforcement, it is now way below the permissible. No? So it's completely fine right now. So now that we have this checks, if I go to the, it seems like our deflection is also correct. No, there's no problem. We go to the different formation. I can see on the deformed shape, can specify the reflected shape or the limits of your deflected shape. And it seems to be just below the limits that we have specified, which is 25 mm. So now that we have this verified and all it's okay, we can now go straight to the report and look into the report. So from the report, you have the options to actually select a brief report, a detailed report, or just the bill of materials. In our case, in this example, I'm going to click on the default, which is detailed, and I'll just generate the report from there. So just give it a few seconds, it will create the report for you. This is quite detailed report, so it generally would take about 10 to 15 seconds to generate. So from here, you can already see the summary. We now have the green check, and use, of course, the summary for the material that we use. We can see it from there, all the values that is required, and the reinforcement, tendons, and you can also see the geometry as well as the loads that we applied, no? And where we applied it. And you can see also the scheme of the reinforcement. And of course, a summary of the results. You can see all the green checks. And not only that, you have much clearer visuals of the stress flow and some tables that you can see that all the calculations are okay. So you have seen all this right there, concrete strength ratio. This actually helps us a lot when we try to submit this, when we try to submit our work to some check-in engineers or agencies that requires us to submit those requirements. So from here, it's much easier for them to understand what is happening into our calculation. So all are there. All those informations are there. So that's basically how we check. And from here, I can stop with my demonstration, and I will go back to my slides. Okay, so get a little bit of a summary. So of course, so in summary, why do we want to use CSFM method? Of course, it's time saving. As you can see, for just a few minutes, we have completed our calculations or code checks. Using strat and time method is not only tedious and iterative process, but it's also time consuming. Accuracy in discontinuity region. So with CSFM, it captures realistic compression and tension fields, while if you compare it to strat and time method, it is highly dependent on the engineer's judgment in choosing the truss model layout. And also sometimes different engineers using different strat and time model, they have possibly different layout as well. And also with CSFM, it covers verification, not just for ultimate limit state, but also serviceability limit state. Lastly, it is code compliance that it supports various codes such as Eurocode, ACI code, and Australian codes. And for the benefit of our newbie attendees that is attending to this webinar, you can also try our program and download it. And you can also try to follow the step-by-step tutorial, which is available from our webpage. So what's next? Again, I would like to invite you to join us in the last episode of this webinar series. The last episode will be entitled Precast and Infrastructure Beams, which is on next month, which will be in September 11. And yeah, that's it. So after the webinar, you will receive a short survey. So please try to fill in the survey. It will actually help us improve our webinar. And of course, you can also suggest in the survey some topics for future webinars that you want to see. Also, the recording will be available in our support center webpage, and it will also be uploaded into our YouTube channel. And if you want to test the application, you may also download a trial version available from our webpage. And lastly, if you're looking for some information regarding the usage of our product, don't hesitate to visit our support and learning center webpage. You can search for knowledge-based articles from there, some tutorials, and some webinars from the past, and probably more. So that's basically the end of this session. So I want to thank you once again for joining me on this webinar, and I hope that we can see you again in the next one. So that's it. Bye-bye.